What we're going to do today is we're going to go ahead and test grounding. You can see how hard this ground is. My earth is right here. By the way, this is my office where I work at, and you'll see the background. And what we're going to do is we're going to drive ground rods down. Actually, we have a whole bunch of ground rods. We're going to coupling them together. We have the proper equipment right here to be able to driving them down. Every 5 feet, we're going to drive the ground rod down. We're going to do a 3-pole fall potential method, and we'll kind of talk about the equipment here. We're going to use a clamp-on meter to check the ground. At the same time, we're going to be using an ammeter to measure the current flow in the event of a ground fault. We're going to take a voltmeter and also test the touch potential. So what we're going to do is we're going to introduce you to my helper. Actually, not a helper. He's been with the utility companies, or electric utilities, right, Joe? For 29 years. And my background with electrical, and Joe Sims' background with the electric utilities. And let's take a look at some of the equipment that we're going to be using here.
Right, Mike. Well, we have a clamp-on grounding tester made by AEMC, which requires no other things other than just to clamp it on. We have a couple of meters there to do our amperage readings. We have our safety equipment, hats, gloves, we have our ground rods, and assorted other small tools.
Okay, now we're going to perform our tests. What I'd like to show you what we have is right now a 10-foot ground rod that's standing up. It's tied on to a ground rod that's 10 foot already driven in the earth. Actually, I'm in danger right now. Now think about it. We have 2 meters that we're checking. On the right-hand side is going to be the amp meter. We'll try to keep that consistent. On the left-hand side is going to be the voltmeter. We see the voltage is about 105 volts, and the amperage is about 0.4 or 0.4 of a milliampere. Now let's see where this current is coming from. If you take a look here, we have an extension cord with 110 volts. It continues over here. It's energizing this rod. This rod is 110 volts. Voltage is going down into the earth. I have the current clamp right on here. That's connected over to the amp meter. So we have 0.4 of an amp, Joe, going directly to the earth at 120 volts. I have the leads of the voltmeter connected to the ground rod, and then I have the other lead of the voltmeter connected directly to the earth. And when I did that, that's when we had about 105 volts. Now I'm going to go back onto the ground rod, and I'm going to take this only about a foot away and stick the one lead into the earth, the red lead. The black lead is onto the ground rod, which is 120 volts, and that gives me about 104 volts. So if I'm only a foot away, I have 104 volts.
Which has a differential.
So that's the difference of potential. So if my knee is on the earth right here, like I'm standing, and if I touch this ground rod, the difference of potential between this ground rod, which is energized, and me is 104 volts. All right, now what I'm going to have you do, and I got to be careful here, we'll turn this power off here right now, is Joe, you're going to check the resistance using the 3-point, and you're going to use the resistance measurement also with the clamp on. So we'll go ahead and get that next.
Okay, now we're going to do our 2 resistance measurements. The first one we're going to do is with the AEMC 3710 clamp-on amp meter, which this meter has both the transmitter and receiver in it. It transmits a signal back out through the system neutral to the power company, into the ground, back through the ground, and up this conductor or grounding electrode, and the meter takes a reading. It knows how much energy it sends out, it knows what frequency it sends it out at, and it looks for that information to come back and makes its measurements. So we're all set up, we're hooked back to system neutral. We'll go ahead and get our meter turned on, and we will clamp on and take our first reading. With this type of equipment, the one thing you have to do is always make sure your CTs are clean.
Can you touch the sides of the CT to the rod? Does that have an effect or not?
Well, they always say is with most CTs that you try to keep it in the middle.
Got it.
We've got the meter zeroed in and it's stabilized and giving us a reading of 265 ohms. This is at 10 foot into the earth.
All right, so now we're going to go ahead and use the 3-point method.
Right. The next thing we'll do is the 3-point fall potential.
Okay.
And we will hook up our 3-point fall potential.
We'll disconnect this from the system neutral.
Exactly. We need just a bare rod.
So when you use the 3-point method, you can only use that one rod, not connected to anything.
That's correct. Okay. So we now have our connection to the rod. With the 3-point fall of potential, we at some distance out in the field there, we have.
Now, 1 second. You had one probe, which was the current probe.
It's the farthest one out.
And you had that at what distance?
It's at 170 feet.
And then we have the potential probe at 62% of that, which was somewhere like around 107 or something like that. We already checked that out to make sure of that.
Right.
Okay, so now we're taking the 10-foot resistance of this ground rod only, not connected to anything else, using a 62% method, which is also called the 3-point method, and it's the fall of potential method. So there are 3 different terms they use sometimes.
Right. We've put our own references in the field.
Now, we're not using a digital meter. This is just simply a method that could be used that's either digital or non-digital. This is just an older type.
Right. So now what we'll do is we'll also transmit a signal of a known energy level and see what we come up with. So I'll just move it off a little bit here so we can sweep it in. So we're taking the bridge and bringing it back to 0. This method obviously is not as fast as a clamp-on, but it's still an accurate method. Okay, now we, on the multiplier scale of 1,000, we're reading 0.38, so that's 380 ohms through this method.
Okay, the clamp-on, I'm writing it down, was 265. The 3-point method was 380 ohms.
Now, it's not uncommon that both these methods don't match because we're using different distances through the soil back to our references.
And they're using different techniques.
Different techniques.
380 versus 265. I guess if I'm looking to get a low resistance and I was going to buy a meter, I'd buy the meter that's going to give me the lowest resistance.
Well, the one thing we want to keep in mind here, this is one rod. We're only 10 feet in the ground.
So as we go deeper, it might change.
Yes, it's going to be lower.
Okay, let's see what happens on the next one. All right, so let's go ahead and go 20 feet then.
Okay.
All right. All right, so now we got, what are we at, 20 feet in there?
20 feet in the ground.
Okay, then we're gonna set this on here, and we'll drive this down on it, and then it'll give us what we use in our reference point.
A nice place to clamp on there.
Okay.
Are we on, now we've got to get a right scale. Okay, 420 mils, 4/10 of an amp. What did it have before?
Same thing as before. We had 4/10 of an amp.
Oh, 4/10.
So we're now at 20 feet.
We just went up a 100th of a...
Well, for our practical purpose,
same
nothing.
thing.
So we didn't change the current flow at all.
It'll be interesting to see what the resistance is.
I agree. Well, let's check it out.
Okay, now we're down at 20 feet.
You connected to neutral.
Connect to neutral.
Use your clamp meter.
I'm going to use a clamp meter.
Now last time, let me make my notes here. I'm not going to tell you what we had last time. That way I don't influence you.
Okay. We're going to stabilize out at about 240 ohms.
240 ohms. I mean, the resistance went from 265 from 10 feet down to 240 at 20 feet. The current, for all practical purposes, didn't change at all.
Okay.
So now we got to check the 3-point and see if that changes.
All right.
Last time it was 380. Let's see if it stays close to that.
We are at basically 300 ohms on the 3-point fall of potential.
300 ohms. Okay.
So we dropped a little there too.
That surprised me because I thought if we doubled the resistance of the ground, we would have significantly reduced that resistance. I'm not surprised on the current flow. I didn't think the ground rod depth would affect the current flow. You take 120 volts directly to the earth at 20 feet, you draw 4/10 of an amp. You're never going to trip a breaker.
Right.
At 10 feet was 4/10 of an ampere. Resistance went down a little bit, but we're nowhere near. We're still over 200 ohms at 20 feet. We're nowhere near the 25 ohms that the code, encourages us to get to.
Right.
All right, we're going to go down to 30 feet. But that was a pretty tough one to drive.
Yeah, that was hard. I would have thought the resistance had dropped a little bit more based on the compactness of the earth.
All right, let's do 30 feet.
Okay.
I really hope that we can drop this goes down a little easier because that was really hard. Okay, I'll put my head down because you don't want me to get any shavings in my eye.
Head down.
Head down.
Let's go.
Okay. Yeah, it's moving. Let me get that for you.
There is a better way. It's a driver that's mounted on a truck.
Yeah.
It has a big slide on it.
I thought that's what you were bringing.
Oh, yeah. right through.
Take it all the way to the top because that's going to be the place that we're going to use it. You know what I'm saying? That's it. Once we get
Now
there.
you can appreciate why it costs so much for somebody to come out and drive grounds.
Yeah, really.
Because you run into unknowns and it takes a while to do it.
I would only pay them by the ohm. What we have right here is we have a ground rod that we've drove already a little earlier this morning, and that's 50 feet. We're going to check the ground resistance on that using the clamp-on meter. And when we're going to finish up the other ground rod on the other side, which is down to 30 feet, and we're just about giving up on that one because that one hit some really hard lime rock or something in the earth. We're going to measure that ground resistance, and then we're going to tie them together, and we're going to find out. And Joe, what do you figure? They're probably about 75 feet apart, 60 feet apart. So we're going to find if we put two ground rods, one 50 foot, we'll find out what the resistance of this one is. The other one 30 foot deep, find out what the resistance of that. Put them in parallel and find out what's the total resistance. How does that work out? So we're going to go ahead and finish up, and then we'll see what happens. All right, we're down to 30 feet. Tough 30 feet. Okay, you're going to put it in 110 volts. Okay, I got my ammeter set to AC. Put it in the little hole. Ooh, man. Our current went up to 1.3 amps. I mean, not a whole lot, but I mean, it's more than 0.4. So 1.3 amperes, and now we're going to check the clamp-on meter and the three-point. Okay. Now we started at 10 feet 265, 20 feet 240, but the amperages did not change. Now at 30 feet, the amperage went to 1.3, which means I would think that amperage was going to go down to 80 amps. Or yeah, I think it's going to go down at least below 100.
Okay, we're at 60, once it stabilizes, 68 ohms.
Okay, I mean ohms. All right, three-point method.
All right, let's do that.
I'll set this to 100, and I'm going to set this around 70.
And this conductor's not...
Actually, this usually is a little higher. I'm going to set it right there, see how it goes. Just get you started. Okay, three-point. Three-point has been high, so I'm guessing this is going to be close to like 100 ohms. Am I good or what?
Yeah, 100 ohms.
100 ohms on the three-point, 68 ohms on the clamp, 1.3 amperes on the current flow. Do you think we can go 40 feet or no? We got that other ground rod we drove 50 feet. You want to just use that one for 50 feet and find out what we get at 50 feet there?
I think we can go another 10 feet.
All right, we'll try one more 10 feet then. I mean, it's really moving. Look at it. I mean, it is flying. I should have made a connection.
Yeah, I think if you were to put another one on, you'd have that same hard spot and then you'd go through. Like you say, run the couplings through the line there.
Yeah, but wouldn't you think the couplings would have broken the line the first, or second, or third time?
I would have thought so, but...
All right, let's do our testing here.
Okay.
Oh, it's on DC? Okay, I'll set that then on AC. Little hole. Whoa, 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 whoa. Now we're up there. We are 5.6 basically. 5.6 amps. Look at my little calculator. If that were true, the resistance then, R being E over I, then 120 divided by about 5.6 should give us a resistance of around 21 ohms. Huh? Oh man, 22.5. You know what? Looks like there's a correlation between this resistance and this current flow. All right, so now if we go with the three-point method, the three-point method's been around 25% higher than the clamp-on, which means if I'm going to predict this, I'm going to predict this on the three-point method, we're going to be around 30 ohms. Hey, so we got a 25 ohms, didn't we?
Yeah,
At least on the clamp-on.
Yeah.
By going 40 feet.
Can't rock it back.
It won't go the other way, huh? No. You're trying to get on the other side, huh? Well, how about 10? Want to rack it back on 10? No. So basically, using a meter like this that's going to be more analog, we get down to those lower resistances, it's really not going to, you're going to have to go to a digital.
At least in this vintage of equipment.
Right.
Yeah.
So you're going to have to go to a digital three-point meter.
Right. I'm sure it would work much more accurately than this. But up to this point, this has been a good
comparison. It's been pretty close.
Yeah. All
right, well, we can't check with here, so we're going to, it looks like the clamp, we can use the clamp as a basis. Now what I'd like to do, we're going to go 50 feet?
Yeah, let's try it.
All right, 50 feet. One more. It's still moving. Okay, 50 feet. I never would have expected that.
That was a hard 50.
It was a hard 50. Wow. 8.1 amperes.
That's looking good.
All right, so now 50 feet, we have 8.1 amperes. I would expect the resistance to be around 15 ohms on the clamp meter. I will just check that now. There you go. I'm guessing, I'm going to use my Ohm's law formula. R is equal to I, 120 over I of 8.11. Mathematically, it'd say it's 15 ohms. And mathematically, this has been really close. So I'm going to say around 16 ohms. 15 to 16. What do we come up with?
16.4.
16.4 ohms. All right. So we have 50 feet. We have 8.1 amperes going to ground at 120 volts, and we have 16.4 ohms, which means that relationship of Ohm's law works. So what I could do is, instead of me actually using these meters, I could drive a ground rod, take 120 volts, measure the current, calculate out the resistance that way, right?
Yep.
The danger is, though, you're dealing with 120 volts and you can get killed, which you don't want to do.
Right.
So either one of these two meters are going to work pretty much effectively. I kind of like that clamp-on meter, though.
Oh, yes. All around, it's hard to beat that meter.
Yeah. All right, let's put them in parallel. Okay, neutral is on. And you're going to check that ground resistance using the clamp meter on that side?
Yes, sir.
This side is a higher resistance than the other side.
Okay, this is the west ground.
This is the west ground at 50 feet. 21.7. Hey, let's take 120 volts to that and see what the amperage is on that.
Okay.
Okay, here we go. Power's on. So we got 120 volts there. I'm going to say it's going to draw about 6 amperes.
5.74.
Is 5.74. We have two ground rods in parallel, and the resistance on the west side right here is 21.7 ohms, and the resistance on the other side was 16.4. And the current flow was 5.7 here and 8.11 on the east side.
Okay.
So let's see what happens to the current flow if we add them together. You ready? All right. 1, 2, 3, power's on. The total current came out to be 13 amperes, which was right, and the resistance is somewhere like around 10 ohms.
And the actual reading is 10.8.
10.8 ohms. So is there anything else we need to check here?
Well, one other thing I would like to do, just for sake of testing, and that is to bring out our calibrator And we'll pick a 12.4 ohm resistance point here.
Yeah, see how close that comes out to be.
Do one last check. Okay, that was 12.4.
It came out to be 12.6.
We're at 12.6.
All right, so
equipment checks out.
There's only one thing I want to do, and that is that what is the touch potential using the ground only with an open neutral at a surface? Since we already have everything set here, all I'm going to do is I'm going to lift the neutral.
Okay.
When I lift the neutral, I'm going to take one load on, I use a hairdryer on, and see what happens to the touch potential with the one ground rod and with two ground rods.
Okay.
Okay? Let me get the hairdryer. Okay, what I have here is I have PVC coming in, 2 hots, and a neutral or a grounded conductor. This neutral is bonded over to this equipment grounding, and I'm going to disconnect my neutral. I'm going to make sure my neutrals and my grounds, power is off. Joe, if you can give me a screwdriver there, maybe it's on top here.
Yes, sir.
My neutrals and grounds, I'll make sure they're tied together. And what I have is I have all the circuit breakers off but one. And I have a hairdryer. And what I'll do is I'll turn on the one load so we have 120 volts coming off the circuit, going to the receptacle right here. That goes over to the hairdryer. The voltage and the current continues and returns back to the hairdryer on the neutral, gets back to the neutral, but since it's lost the return path, it connects over to the ground. And what we have now, the ground is connected to the case, which is connected to the metal structure of this building here. I'm going to have touch potential. And I want to find out is, if it's properly grounded, what's the touch potential with 2 ground rods, like we have the 2 50-foot ground rods, or 1 ground rod, and what that value is going to come out to be. So we'll check that out in a second. Let's get the right circuits. Okay, Joe, go ahead and turn on the hairdryer, 1800 watt hairdryer. Go ahead, turn it on.
Low speed.
Go ahead. All right, Bruce, if we take a look at the voltage here, we're operating at about 8 volts, which is this metal parts of the earth. Go ahead and turn it on the other speed. Now we jump up to 20 volts. So if we lose a neutral, the metal parts of all the building becomes energized relative to the earth. All right, let's cut one of the grounds off and see what happens. We have 1 ground rod at 21 ohms. Our voltage is 15.8, where before it was lower than that. And now go to the other speed. Now we're going over 30, I think it was 24. So as we reduce the earth resistance and you lose a neutral, the touch potential increases. So we really want to have a good ground, a very low resistive ground, because it does provide a reduction in touch potential. Okay, let me summarize what we've done here, Joe. Looks to me like when we went to 10 feet, we had like around 300 ohms, 20 feet, 300 ohms. The current traveling to ground, direct 120 volts to that ground rod, was about a half an ampere, actually 4/10 of an ampere.
Right.
We had the touch potential, was still 120 volts. You could get killed even if you had a ground rod. That's not going to solve it.
Right.
Went to 30 feet, we started dropping down to 1.3 amperes, and that resistance went down close to anywhere between 68 and 100 ohms, depending upon the meters that you use. Let's say around 75 ohms or so.
Okay.
When we went to 40 feet, that's when there's a big drop down. The resistance went down below 25 ohms.
Right.
But our current was still only 5.6 amperes, which is basically works out that Ohm's law, I is equal to E over R, 120 over the resistance. We got down to 50 feet. We dropped down some more resistance, down to 16 ohms, which was pretty good. Our current went up to 8.11. And then we had 2 ground rods, the east side, which was 16 ohms, the west side, which 50 feet, which was 21 ohms. We put them in parallel. That resistance went down to 10.8 ohms. Again, right. I'm really surprised. I'm really surprised. And I didn't think that the clamp-on ground resistance measurement could possibly work. I really didn't. And I thought the 3-point method, I thought that whole thing was a little spooky anyhow. I thought, you know, that was going to work.
Well, there is some limitations depending upon what direction you go in.
Yeah, and the soil resistivity and everything. But bottom line, it looks like, you know, you could put an amp meter on there and take 120 volts, measure the current, figure out that resistance.
Right.
But it's too dangerous.
Right.
So if you use the 3-point method, or if you use the clamp method, either one's fine. And then it's a matter of, I guess, convenience. If you couldn't afford the clamp on, and you don't need to test it that often and that variety of them, and you only need to do a few ground tests,
right.
the 3-point method would be fine.
if you have the time and the space, if you're not limited by concrete and asphalt.
That's right.
You get inside of a building and there's only one way to do it.
Oh, I see what you're saying. If you're trying to measure a ground rod in a building,
Yeah, I've run into that a lot.
or you have a yard that's only 75 by 100.
Exactly. There's
All right, so both of them work
limitations.
fine, and it's just a matter of cost, convenience, and features.
Time.
And time. And time is a big factor to take.
It takes a lot of time, 3-point fall potential.
Okay. Touch potential reduced when we had better grounds,
Yes. A little.
but we still didn't trip a breaker.
No.
We had two 50-foot ground rods tied together. We only drew, I think it was about 13.24 amperes.
Right.
Well, I think that's it for now. We're done, guys. We'll see what happens in the future.
Stay tuned.